So today we're going to be doing October-November 2022 paper 11. Question number 1 says, which sample contains the same number of the named species as the number of molecules in 35.5 grams of chlorine? Now we know that the number of molecules is just proportional to the number of moles, right? What we can do here is we can first figure out the number of moles of chlorine molecules that we have in 35.5 grams of chlorine. Now chlorine, right, the molecule has an MR of 71, right, because each chlorine atom is 35.5, so that means the number of moles is 35.5 divided by 71, right? That's just the mass divided by the MR. 35.5 divided by 71, which is 0.5 moles. Okay, so we have 0.5 moles of chlorine molecules. So they're saying, okay, if you look at these species over here, which of them is exactly 0.5 moles of that given substance, right? So let's start with option A, atoms in 16 grams of sulfur. Now sulfur has a relative atomic mass of 32.1, which means that the number of moles is the mass divided by the relative atomic mass in this case, right, which is 16 divided by 32.1. So that is 0.5 moles of atoms. So that means that the answer over here is just A, right? We have 0.5 moles of sulfur atoms here, and we have 0.5 moles of chlorine molecules in the 35.5 grams of chlorine. So we have an equal number of atoms of sulfur here as we do molecules of chlorine in 35.5 grams. So the answer is A. Question number 2 says mixture R consists of 1 mole of C3H6 and 1 mole of C4H6. What is the minimum number of moles of oxygen molecules needed for complete combustion of mixture R? So in mixture R, we have 1 mole of C3H6 and 1 mole of C4H6. Okay? And we want to figure out how many moles of oxygen we need for complete combustion. So the first thing you would do here is you write down the equation for the complete combustion of C3H6 and C4H6. Okay? So C3H6, when it's completely combusted in oxygen, we get carbon dioxide and water, right? So CO2 and H2O. And over here, right, we have 1 mole of C3H6. That means that on the right hand side, we're going to have 3 moles of carbon dioxide, right? The carbons have to balance. Then we have 6 hydrogens on the left. So we're going to need 3 H2O. And then over here, we have 3 times 2, that's 6 plus 3, that's 9. Right? We have 9 oxygens. We get 9 over 2 O2. Next, we write down the equation for the combustion of C4H6. Right? C4H6 reacts with oxygen to form again CO2 and H2O. Right? And here, again, we have 1 mole of C4H6. So we're going to have 4 CO2, 4 carbons on the left, so 4 on the right. We have 6 hydrogens on the left, so we're going to need 6 on the right. So that'll be 3 H2O. And then we have 4 times 2, that's 8, plus 3, that's 11 oxygens. So that would be 11 over 2 O2. 11 oxygen atoms would mean 11 over 2 O2, right? The number of moles of oxygen we need is 9 over 2 plus 11 over 2, which is 20 over 2 or 10. Okay, this is 4.5 plus 5.5, okay, which gives us 10 moles of oxygen. Which statement about the electrons in a ground state carbon atom is correct? So let's actually write down the electronic configuration of carbon in the ground state, right? Carbon has 6 electrons. It has 6 electrons, atomic number 6. So the configuration is 1s2, 2s2, and then 2p2. Now option A says electrons are present in 4 different energy levels. That's not true, right? Only the first and second shell are occupied. When we say energy levels, we're talking about shells, right? This just means shells. And here we just have 2 shells, so that's incorrect. Option B says there are more electrons in p orbitals than there are in s orbitals. That's not true. So there's only 2 electrons in p orbitals, but there's 4 in total in the 2 s orbitals. The occupied orbital of highest energy is spherical. No, the highest energy orbital is the 2p orbital. That is a dumbbell shaped orbital. So the answer is D. The occupied orbital of lowest energy is spherical, right? That's the 1s orbital. It has a spherical shape. For the element sulfur, which pair of ionization energies has the largest difference between them? Sulfur is in group 16, the same group as oxygen. So that means it has 6 valence electrons, okay? It has 6 valence electrons. It has 6 valence electrons. So when you're removing these valence electrons, right, the first 6 electrons that you remove will be removed from the valence shell, whereas the seventh electron will be removed from a shell closer to the nucleus. So the first six are going to be relatively easy to remove, whereas the seventh one will be much more difficult to remove. So there's going to be a big jump from the sixth to the seventh ionization energy, right? 6 valence electrons, relatively easy to remove, and then the seventh electron is going to be removed from an inner shell. So there's going to be a big jump between the sixth and seventh ionization energies. How many sigma bonds are present in one of these molecules? Now remember, any single bond will be a sigma bond, right? And when we talk about double or triple bonds, right, there's only one sigma bond, whereas every additional bond is a pi bond. So this triple bond, there's one sigma and then 2 pi bonds, right? And the double bond, we have one sigma and 1 pi bond. So again, there'll always be only one sigma bond, okay, between these atoms. So here we have 1, 2, 3, and then this carbon is bonded to this carbon, that's 4, and this carbon is bonded to 3 hydrogens, so that's 7, and then this carbon is making one sigma bond to this carbon, that's 8, and this carbon is bonded to a hydrogen, that's 9, it's bonded to this carbon, that's 10, and then this carbon is bonded to 3 hydrogens, so that is 13. So there are 13 sigma bonds. Which molecule has an equal number of bonding electrons and lone pair electrons? Now let's go through each of the options, right? BH3 is this boron making 3 bonds with hydrogen, right? And boron is in group 13, so it only has 3 valence electrons. Right? Boron. And each of those 3 valence electrons is bonded. So there are no lone pairs here. Whereas there are 3 bonded pairs here. So it's not A. If you look at option B, that's carbon dioxide, right? Carbon dioxide is C double bonded to 2 oxygens, right? And each oxygen has 6 valence electrons. 2 of them are bonded, whereas each oxygen also has 2 lone pairs. Okay, so here the total number of bonding electrons, each bond has 2 electrons, so that's 2 plus 2, 4, and then 8, right? You have 4 electrons in each of these double bonds, so that's 8 electrons that are bonded, and you have 4 lone pairs, 2 on each oxygen, so that is 8 electrons in lone pairs. So here you have 8 bonding electrons and you have 8 lone pair electrons in carbon dioxide. The table shows properties of 4 solids held together by different types of bonding. Which row correctly describes the properties of a solid with a giant covalent structure? So something that has a giant covalent structure will have a very high melting point. And it's going to be insoluble in polar solvents. So an example of a polar solvent would be H2O, for example, right? So you think about things like diamond, or you think about silicon dioxide, that's sand, right? They are insoluble in polar solvents such as water. So the answer is A. The carbonate of an S block element is reacted with an excess of hydrochloric acid. 0.833 grams of the carbonate releases 200 centimeter cube of gas, measured under room conditions. What is the identity of the metal carbonate? When we decompose these metal carbonates, right, we get the oxide and carbon dioxide. Right? So that's the gas that's being produced. The gas that's being produced is carbon dioxide, and the volume is being measured under room conditions, so we can find the number of moles of carbon dioxide. Number of moles of carbon dioxide is equal to the volume divided by 24,000. Right? This is the molar volume of a gas in centimeter cube. And the number of moles of carbon dioxide will be 200 divided by 24,000, which is equal to 0.00833 moles. So that's how many moles we have of carbon dioxide. Now, can I say that the number of moles of carbon dioxide is equal to the number of moles of the carbonate? The reason why is because 1 mole of every carbonate will give us 1 mole of carbon dioxide. So if I had 1 mole of sodium carbonate, I'd get 1 mole of carbon dioxide. Same for potassium, same for magnesium carbonate, same for calcium carbonate. Right? Each of these would decompose 1 mole of each of these would decompose to form 1 mole of carbon dioxide. So however many moles of carbon dioxide we have, that's the number of moles of carbonate that we have. So once we know the number of moles of the carbonate and we have the mass of the carbonate, we can find the MR, or the molar mass of the carbonate. We know that the number of moles is equal to the mass divided by the molar mass, which implies that the MR, or the molar mass, is equal to the mass divided by the number of moles. So that would be 0.833, that's the mass in grams, divided by the number of moles, that's 0.00833 moles. So the MR of the carbonate is 100. Now in each of these carbonates, we just have one CO3, okay? CO3 has a mass of 60, which means that the metal over here will have a mass of 40. So the metal will have a mass of 40 in 1 mole of the carbonate. So over here, we know that the relative atomic mass of calcium is 40.1. So that's the answer. Okay, the answer is calcium carbonate. Calcium is 40.1 plus carbonate is 60. So we get an MR of 100.1. The enthalpy change of formation of both PCl3 and PCl5 are exothermic. PCl3 reacts with chlorine. Which pair of statements is correct? Delta H reaction is less negative than the enthalpy change of formation of PCl5. And statement 2 says the Cl2 bond energy is needed in calculating delta H reaction from enthalpies of formation. Now we know that statement 2 is incorrect. Statement 2 is incorrect over here in option A, because if you have enthalpies of formation, right, we can just say that the enthalpy change of the reaction is just the enthalpy change of formation of the products minus the enthalpy change of formation of the reactants. And we know that chlorine is an element in its standard state, so the enthalpy change of formation for chlorine is just 0. So we don't need the bond energy for chlorine if we want to calculate the enthalpy change of the reaction from the enthalpies of formation. As long as we have the enthalpy of formation of PCl5 and PCl3, we can calculate the enthalpy change of the reaction, which means that option B is also incorrect. Now option C says delta H reaction is less negative than the standard enthalpy change of formation of PCl5. Now the enthalpy change of the reaction is negative 124. It's negative 124. What does that tell you about the enthalpy change of formation of the products and the reactants? Which of these values is more negative? They've mentioned that the enthalpy change of the formation for both of them are exothermic. So we know that they're both negative. We know that the enthalpy change of formation for both of them, is negative. But which of them would be more negative over here? The enthalpy change of formation of PCl5 would be more negative, right? Because we're taking this negative value, that's for PCl5, and then we're subtracting the enthalpy change of formation of PCl3. Again, PCl5 is your product, right? PCl5 is your product and PCl3 is your reactant, right? Now, if you subtract a negative value, this term becomes positive, right? This term over here becomes positive. And if the overall enthalpy change of the reaction is negative, it means that if I take this negative value, and I make it less negative, or I add a positive value to it, then I get negative 124. I'll repeat. If I take this negative value, and then I subtract this negative value, in other words, I'm adding a positive value. So I take this negative value, I make it less negative, I get negative 124. In other words, the enthalpy change of formation of PCl5 must be more negative than the enthalpy change of the reaction, or we can say that the enthalpy change of the reaction is less negative than the enthalpy change of formation of PCl5. A student mixes 25 cm³ of 0.35 mole per dm³ sodium hydroxide solution with 25 cm³ of 0.35 mole per dm³ hydrochloric acid. The temperature increases by 2.5 degrees Celsius. No heat is lost to the surroundings. The final mixture has a specific heat capacity of 4.2 joules per centimeter cube per Kelvin. What is the molar enthalpy change for the reaction? Now over here we have a reaction with sodium hydroxide and hydrochloric acid. This is a neutralization reaction. It's a neutralization reaction. So this enthalpy change that we're talking about is the enthalpy change of neutralization. Okay, so we have HCl reacting with NaOH to give us NaCl and H2O. Okay, and we have to find the enthalpy change. We have to find the enthalpy change for every 1 mole of water produced. We find the enthalpy change for every 1 mole of water produced. Now we know that the number of moles of HCl is the concentration times the volume. Concentration is given to us 0.35 and the volume is 25 cm cube, so that's 25 over 1000 decimeter cube, which gives us the number of moles as 0.00875 moles. So that's the number of moles of HCl. We have the same number of moles of NaOH, right? Because we're using the same concentration and the same volume here for NaOH. And that means that 0.00875 moles of water are being produced, right? Now we need to find the enthalpy change for 1 mole of water being produced, right? Enthalpy change in neutralization is for 1 mole of H2O being produced. Okay, so here we first need to find the heat energy released in this reaction. We can do that by using the formula Q is equal to mc delta T, right? The mass of water is just 50 grams because we're mixing 225 cm cube solutions, right? Remember that water has a density of 1 gram per cm cube, so the volume in centimeter cube is the mass in grams. So here we're going to have the mass of water, which is 50 grams because 50 cm cube of water. So that's 50 grams of water. The specific heat capacity is 4.2 and the change in temperature is 2.5. So we get Q as 525 joules. Now we want our answer in kilojoules per mole. So let's first convert this to kilojoules. That would be 0.525 kilojoules, right? We can just divide the answer in joules by 1000. Now this is the amount of heat released. This is the amount of heat released for this many moles of water being produced. When we talk about the enthalpy change of neutralization here, over here, right? What we can say over here is that the enthalpy change of neutralization is minus Q divided by N, where N is the number of moles of water. Again, if Q is positive, it means that the reaction is releasing heat, so the enthalpy change would be negative. It's an exothermic reaction. So we're going to take minus Q, and we want it per mole of water, so we divide it by the number of moles of water being produced. So we get negative 0.525 divided by 0.00875, and that gives us the answer as negative 60 kilojoules per mole. Okay, negative 60 kilojoules per mole. Okay, so that's the answer. So the answer over here is B. Okay, the answer over here is B. Ammonium ions are converted into nitrate ions by bacteria. What is the change in the oxidation number of nitrogen? So let's start with ammonium ions, right? Ammonium ions are NH4 plus. What's the oxidation number of nitrogen in ammonium ions? Let's say that the oxidation number is X. Okay, we have 4 hydrogens, each of which have an oxidation number of +1. Remember, when hydrogen is bonded to a non-metal, it has an oxidation number of +1. And then the overall oxidation number is just +1. That's the charge on the ion. So that gives us the oxidation number of nitrogen in the ammonium ion as -3. We have +1 minus 4. So the oxidation number of nitrogen in ammonium is -3. And then the nitrate ion is NO3 minus. Okay, let's say that the oxidation number of nitrogen over here is Y. We have 3 oxygens, each of which is -2. And then the overall oxidation number for the nitrate ion is just the charge on the nitrate ion, that's -1. So that gives us the oxidation number of nitrogen as +5. Okay, so the oxidation number of nitrogen in the nitrate ion is +5. So the oxidation number is going from -3 in ammonium to +5 in nitrate. So that's a change of +8. It's increasing by 8. So the answer is C. Sodium dichromate 6 reacts with hydrogen peroxide, producing chromium 3 ions, Cr3+, water, and oxygen. What is the correctly balanced ionic equation for this reaction? Now this equation is a little bit trickier to balance, okay, because the chromium here, right, the chromium over here is being reduced. It's going from +6. It's going from +6 to plus 3, and the oxygen in hydrogen peroxide is -1, right? That's the oxidation number of oxygen in peroxides, whereas in water it's -2, okay? Whereas in water oxygen is -2, okay, and in oxygen gas it's 0, right? So we can clearly see that the oxygen in the hydrogen peroxide, right, is undergoing both reduction and oxidation. It's increasing from -1 to 0 in oxygen, and it's decreasing from -1 to -2 in water. So this will be a tricky equation to balance using changes in oxidation numbers. But another thing that has to be balanced are the charges on both sides of the equation, right? The charges on both sides of the equation have to be balanced, the number of atoms have to be balanced on both sides. So here we have 2 chromium atoms on both sides, right? We have 7 plus 2, that's 9 oxygens here, and we have 2 plus 8, 10 oxygens over here. So the oxygens aren't balanced, the number of atoms aren't balanced in the first equation. In the second equation, we can check if the number of atoms as well as the charges are balanced on both sides. We have 2 chromium atoms on both sides. We have 7 oxygens here, plus 2 times 3, that's 6. So 7 plus 6 is 13. And then over here we have 7 plus 6, that's 13 oxygens as well. Right? We have 8 plus 6, that's 14 hydrogens. We have 7 times 2, that's 14. And then if you look at the charges, we have 2 minus plus 8 times 1 plus, that's plus 6. And then on the right hand side is 2 times plus 3, that's plus 6. So the charges are balanced on both sides. So in this case, the atoms and the charges on both sides of the equation are balanced. So the answer is B. In which equilibrium reaction is the position of equilibrium moved to the right hand side by increasing the temperature and also by decreasing the pressure? So if the equilibrium moves to the right hand side when we increase the temperature, what does that tell us about the enthalpy change of the reaction? It favors an increase in temperature. It favors an increase in temperature, which means that the forward reaction is endothermic, okay? The forward reaction must be endothermic because the equilibrium is moving to the right in the forward direction if we increase the temperature. So we know that the answer has to be A or B. And the yield is increased by decreasing the pressure. What does that tell you? Now an increase in pressure favors the side with fewer moles of gas. So a decrease in pressure favors the side with more moles of gas. Okay, I'll repeat. An increase in pressure favors the side with fewer moles of gas. So a decrease in pressure favors the side with more moles of gas. So here the decrease in pressure favors the right hand side. There are more moles of gas on the right hand side, which means that the answer is B. There's an equal number of moles of gas on either side in A, whereas in B there are more moles of gas on the right hand side. Ethanol is produced industrially by reacting ethene and steam. So here they've shown the reaction between ethene and steam to form ethanol. The Kp has a value of 1.8 into 10 to the power -5, and the partial pressure of the reactants at equilibrium are shown. Which row is correct? We have to find the partial pressure of ethanol at equilibrium and the units of Kp. So the Kp for this reaction is going to be the partial pressure of ethanol, divided by the partial pressure of ethene times the partial pressure of H2O. Right over here, we're going to have the partial pressure of the products to the power of their coefficients. So the coefficient for ethanol is just 1. And then we're going to divide it by the partial pressures of the reactants, right? The product of the partial pressures of the reactants to their stoichiometric coefficients, raised to their stoichiometric coefficient, which is 1 in this case as well for ethene and water. So that means that Kp, which is 1.8 into 10 to the power of -5, is equal to the partial pressure of ethanol. That's what we want to find. Let's call that X. Divided by the partial pressure of ethene. That's 4.8 into 10 to the power of 3. Multiplied by the partial pressure of steam, which is 2.8 into 10 to the power of 3. And that gives us the partial pressure of ethanol as 242 kilopascals. Right, those are the units that we're using here. So the answer is A or B, right? 2.42 into 10 to the power of 2. And then the units for Kp are pressure divided by pressure squared, right? We have pressure in the numerator and we have pressure times pressure in the denominator. The units over here are 1 over P, which is 1 over kilopascals, which is kilopascal inverse. So the answer is A. So the answer is A. A large excess of magnesium ribbon is added to dilute hydrochloric acid and the volume of hydrogen gas produced is measured as the reaction proceeds. The reaction is exothermic. The results are shown. Which row explains the changes in the rate of reaction between points P and Q and between points Q and R? So here we have a reaction between magnesium and hydrochloric acid, and we're making magnesium chloride and hydrogen gas. We're going to have 2HCl over here, and the enthalpy change for this reaction is negative. It's an exothermic reaction. Now, usually for a reaction, the rate is fastest at the beginning, right? The rate is fastest at the beginning. We can find the rate by simply looking at the volume of gas produced per unit time. So that would be the tangent, right? The volume being produced per unit time. So that would be the slope of this graph. In other words, the slope of the tangent. So this is the initial rate, whereas the rate over here is actually faster, right? The graph is getting steeper, so the rate is increasing. So the rate increases over time initially, and then it slows down again. So why does the rate increase as the reaction proceeds? Why is it not fastest at the beginning? As the reaction is taking place, it's an exothermic reaction. So the reaction is releasing heat. What is this heat being released do to the rate of the reaction? As the reaction container or the contents warm up, what does that do? What does that do to the rate of the reaction? It increases the rate of the reaction. The heat being released increases the rate of the reaction, right? The reason why is because as heat is being released, it increases the temperature of the surroundings or the temperature of the contents of the container, right? And because of this increase in temperature, we see an increase in rate initially, right? We see an increase in rate as the reaction proceeds. So the increase in temperature explains why the graph is becoming steeper between points P and Q. It explains why the graph is becoming steeper between points P and Q. Okay, so the reaction temperature is increasing. Despite the concentration of the HCl decreasing and the amount of magnesium decreasing, despite their amounts decreasing, the rate is increasing because of an increase in temperature. And then between points Q and R, the acid concentration is falling. We wouldn't say the magnesium has been used up. The reason why is because we're using a large excess of magnesium ribbon. We're using a large excess of magnesium ribbon, right? It means that we're going to have magnesium left over. So because the acid concentration is falling, as the concentration decreases, eventually the rate of the reaction decreases. So the graph levels off. So between points Q and R, the acid concentration is falling, which is why the rate of the reaction is decreasing. Measurements are made to determine the activation energy, EA, of a reaction. The diagram shows EA on the Boltzmann distribution at temperature T1. Measurements are then made at a higher temperature T2, which diagram correctly shows the Boltzmann distribution and the activation energy at T2. Now, if I increase the temperature, does it affect the activation energy at all? No, it doesn't, right? Only a catalyst affects the activation energy. So the activation energy will remain the same. So there's no change in the activation energy, which means that option B is incorrect and option D is incorrect, right? Option B is incorrect and option D is incorrect. And then if you look at the graph, what does an increase in temperature do? What does an increase in temperature do to this graph? Does it shift the curve to the right or the left? It shifts the curve to the right. Right? The curve becomes flatter and it shifts to the right. The peak shifts to the right, which means that now there are more molecules that have energy greater than the activation energy. So initially it was only these molecules that were reacting, right? It was only these molecules over here that were reacting, but at higher temperature we'll have more molecules that can react. So the answer over here is A, right? The curve shifts to the right, becomes a bit flatter, and there's a greater number of molecules that now have energy greater than or equal to the activation energy. So the area under the curve past the activation energy to the right of the activation energy increases. The electrical conductivities of two compounds Y and Z are shown. Y is a good conductor in the liquid state, whereas Z does not conduct in the liquid state. When we talk about the conductivity of the mixture obtained by adding the compound to water, in other words, when we add Y and Z to water, we get an aqueous solution. Y is a good conductor in solution in the aqueous state, and Z is also a good conductor. What are compounds Y and Z? First of all, Y is a good conductor in both the liquid and the aqueous state. So if it's a good conductor in the aqueous state, what does that tell you about Y? What type of a compound is it? Y must be an ionic compound, right? Y must be an ionic compound. And then if it's a good conductor in the aqueous state, what does that tell you about the solubility of Y? Does it dissolve to form ions or is it insoluble? Y must be soluble, right, in water. It's soluble in water, it dissolves to form aqueous ions. So Y is ionic, right? Y is ionic and it's soluble in water. So it can't be aluminum oxide. Aluminum oxide will conduct in the molten state because it's an ionic compound. However, it doesn't dissolve in water. So it won't form ions in solution. Okay, won't form enough ions in solution. So it's not going to be a good conductor in aqueous solution. Sodium chloride, on the other hand, is ionic and it dissolves in water to form a solution. Okay, and then Z does not conduct in the molten state or the liquid state. So Z is not ionic, right? The type of bonding in Z is covalent. So it can't be aluminum oxide, which leaves the only option as silicon 4 chloride or silicon tetrachloride. And the reason it conducts electricity in aqueous solution is because SiCl4 is hydrolyzed by water. Okay, it undergoes hydrolysis. So it reacts with water. It reacts with water to form silicon 4 oxide or silicon dioxide, that's SiO2 and HCl, right? HCl. This is H plus and Cl minus. And let's balance this also. We have 4 HCl over here and we're going to have 2 H2O. Okay, so this HCl, this guy over here, right? We have H plus and Cl minus ions in solution, right? This is why the aqueous solution conducts electricity, even though it is a covalent compound. Because it undergoes hydrolysis, we get a precipitate, a white precipitate of silicon 4 oxide, and we get an aqueous solution of HCl. We're also going to observe white fumes of HCl being produced, right? So some of the HCl will be given off as vapor, as hydrogen chloride, whereas some of it will remain dissolved in solution. Which row describes the relative sizes of the ionic radii of sodium ions, Na+, magnesium ions, Mg2+, and sulfide ions, S2-. Now, Na+ has a total of 10 electrons, right? Sodium atoms have 11 electrons, but it's lost an electron, so it has 10 electrons. Whereas magnesium has an atomic number of 12, so magnesium atom has 12 electrons, whereas Mg2+ has 10 electrons. Okay, it has 12 electrons, 2 of them are lost, so we get 10 electrons. And then sulfide has a total of 18 electrons. The sulfur atom has 16, and then it's gained 2 electrons, so we have 18 electrons. So for sodium, again, 11 electrons in the atom, 1 is lost. For magnesium, 12 electrons in an atom, 2 are lost. And then for sulfur, for the sulfide ion, 16 electrons in an atom of sulfur, and then 2 are gained. So which of these do you think is the largest? So we can say because the sulfide ion has 18 electrons, there are 3 shells over here, right? There's 3 shells over here. So we know for a fact that this will be the largest of the 3 ions, right? Sodium and magnesium ions only have 2 shells. Okay, we only have 2 shells over here. So we know that the sulfide ion will be the largest, which leaves us with options A and B. Now, which of these two is smaller and which of these two is larger? So let's compare sodium and magnesium. The ions, they both have 10 electrons. Now sodium has 11 protons in the nucleus, right? And magnesium has 12 protons. They have the same configuration. Both ions have the same configuration. They have the same number of electrons, same electronic configuration. The only difference over here is the number of protons. Magnesium has more protons, which means that the valence electrons are being held more strongly, right? They're experiencing a greater nuclear attraction. So we have a greater number of protons for magnesium, right? Greater number of protons, which means that we have a smaller radius. Okay, again, the greater the number of protons, the more strongly the electrons are being attracted towards the nucleus. Okay, so the smaller the ion. So the smallest over here will be Mg2 plus, and the largest will be the sulfide ion. So the answer is B. The oxides, barium oxide, calcium oxide, magnesium oxide, and strontium oxide all produce alkaline solutions when added to water. Which oxide produces a saturated solution with the highest pH? In other words, which oxide produces the most alkaline solution? When we talk about saturated solution, right, we're talking about how much of each oxide dissolves. So which of these oxides is the most soluble? Which of these oxides is the most soluble? The solubility of the group 2 oxides increases down the group. The solubility of the group 2 oxides increases down the group. So we have magnesium, calcium, strontium, and barium, right? And what happens is that down the group, if we take the metal oxide, right? So because the metal oxides, right, the metal oxides react with water to form the metal hydroxide, right? And the greater the solubility, the greater the concentration of the hydroxide in aqueous solution. Now, since barium oxide is the most soluble, it will result in the greatest concentration of hydroxide ions in aqueous solution and therefore the highest pH. So a saturated solution of barium oxide dissolved in water, in other words, a saturated solution of barium hydroxide will be the most alkaline. Which row is correct? The temperature needed to decompose group 2 metal nitrates, does it decrease down the group or increase down the group? The thermal stability of group 2 nitrates and carbonates increases down the group. The thermal stability increases down the group, right, for the group 2 nitrates and carbonates. So down the group, we need a higher temperature to decompose the metal nitrates. So the temperature needed for decomposition increases down the group because the nitrates down the group are more thermally stable. What about the solubility of the sulfates? The solubility of the sulfates decreases down the group. Okay, it decreases down the group. So of these four, magnesium sulfate would be the most soluble, and barium sulfate would be the least soluble. So the answer is D. Question number 21 says, which statement about group 17 elements and compounds is correct? So this question talks about the reducing strength of the halides, right? It talks about the reducing strength of the halides. Specifically, we're comparing chloride and bromide. Now you might remember that down the group, the reducing strength of the halides, the anions of the halogens, increases. So bromide is a stronger reducing agent than chloride, right? When we talk about the reducing strength, bromide is a stronger reducing agent than chloride, right? So chloride cannot reduce concentrated sulfuric acid. In other words, it is not oxidized by concentrated sulfuric acid. Okay, it's not a strong enough reducing agent for this. Similarly, again, because chloride is a weaker reducing agent than bromide, right, it will not react with bromine. Okay, chloride is a weaker reducing agent than bromide, so it will not react with bromine. Okay, so it will not undergo oxidation to form chlorine. So it's not A or B. Okay, C is correct. Okay, bromide is a strong enough reducing agent to reduce concentrated sulfuric acid, or because it's a stronger reducing agent, it undergoes oxidation more easily, so it can be oxidized. It can be oxidized by concentrated sulfuric acid from bromide to bromine. So the answer over here is C. Okay, the answer over here is C. And then D is obviously incorrect as well because bromide is a weaker reducing agent than iodide. So it is not able to reduce iodine. Okay, bromide will not react with iodine because iodide is an even stronger reducing agent than bromide. So D is also incorrect. So the answer here is C. Chlorine is bubbled through 100 cm cube of hot 4 mole per dm cube sodium hydroxide until the reaction is complete. Which row is correct? So here they're asking for the coefficient for chlorine in this equation and the concentration of the sodium after the reaction is complete. Now the initial concentration is 4 mole per dm cube. The total amount of sodium ions remains unchanged. The total amount of sodium ions remains unchanged, right? Whatever sodium we had at the start of the reaction, we have the same amount of sodium at the end of the reaction. So the number of moles of sodium ions remains unchanged, right? We want to know if the concentration is changed or not. Now by adding chlorine to this mixture, what are we doing to the volume? Remember, the concentration is just number of moles divided by volume. So what are we doing to the volume of this mixture as we bubble chlorine through it? As chlorine is bubbled through the solution, right? As chlorine is bubbled through the solution, what we see is that water is being produced. Water is being produced, and the formation of water results in an increase in the volume of the solution. It results in an increase in the volume of the solution, right? The number of moles of sodium remains the same, but the volume of water increases, which means that the concentration decreases. Again, we have the same number of moles of sodium, right, on the left and the right hand side. However, because we have more moles of water after the reaction is complete, we have a greater volume of water, which means a lower concentration of sodium. So the concentration decreases. The concentration decreases. And then as far as balancing the equation is concerned, right, we should know that this is a disproportionation reaction in which the chlorine is being oxidized from 0 to +5 and it's being reduced from 0 to -1. Right? So we're going to need 5 chlorines. We're going to need 5 chlorines to be reduced by -1 for every 1 chlorine to be oxidized by +5. Again, the overall changes in oxidation numbers have to balance. So 5 chlorines decrease by -1, that's a total decrease of -5, and then 1 chlorine increases by +5. So -5 and +5 balance each other out. So we have 5 plus 1, that's a total of 6 chlorine atoms. So that would be 3 Cl2. So X is 3, which means that the answer over here is B. Which statement about ammonia or the ammonium ion is correct? Ammonia gas is produced when an aqueous solution containing the ammonium ion is reacted with a strong acid. That is incorrect, okay? The ammonium ion is acidic. The ammonium ion is acidic, so it reacts with alkali, okay? It reacts with alkali to produce ammonia, okay? It doesn't react with acids, it would react with alkali. So option A is incorrect. Silver iodide is not soluble in concentrated ammonia, okay? So this is also incorrect. Okay, silver iodide is soluble in concentrated aqueous solution of ammonia. That is incorrect, okay? It doesn't dissolve in dilute or concentrated ammonia. The ammonium ion has the same number of electrons as a methane molecule. The ammonium ion has the formula NH4+, right? Nitrogen has 7 electrons. Hydrogen has 1 electron. We have 4 of those, so that's 4 electrons, and it has a positive charge. So it's lost 1 electron. It has lost 1 electron, which means that the total number of electrons in ammonium is 10, right? There's 10 electrons here. And in a methane molecule, right, carbon has 6 electrons, and then each of the hydrogens has 1. So that's 6 plus 4, that is again 10 electrons. So yes, ammonium and methane both have the same number of electrons. Statement D is incorrect because the ammonium ion is tetrahedral. Okay, it is not square planar. Okay, the shape of the ammonium ion is tetrahedral. Sulfur dioxide can be catalytically oxidized by an oxide of nitrogen in the atmosphere. Which reaction shows how the catalyst is reformed? Now, as far as this reaction is concerned, okay, when sulfur dioxide is oxidized by an oxide of nitrogen in the atmosphere, right, it can be oxidized by nitrogen monoxide or by nitrogen dioxide, okay, but both steps of the reaction will always involve oxides of nitrogen. So both oxides of nitrogen have to be involved. Okay, so the answer has to be D. Okay, and I'll show you how this works. Okay, so nitrogen dioxide can catalyze the formation of sulfur trioxide. In this case, your nitrogen dioxide first reacts with SO2 and we get nitrogen monoxide, and sulfur trioxide, and then the nitrogen monoxide reacts with oxygen in the atmosphere, and you regenerate the catalyst. Okay, you regenerate the catalyst. So you can see here that the catalyst is being regenerated, right? And nitrogen monoxide over here is the intermediate. Okay, and the overall equation for this reaction, is SO2 plus half O2 gives us SO3. Again, for the overall equation, we're just adding reactions 1 and 2. Okay, if we add reactions 1 and 2, what you'll see is that NO2 on the left and NO2 on the right cancel each other out, and NO on the right and NO on the left also cancel each other out. So the overall equation is just SO2 plus half O2 gives us SO3. And we can clearly see that this equation, this reaction over here between nitrogen monoxide and oxygen, is part of this process. So the answer here is D. Now, nitrogen monoxide can also catalyze this reaction. Nitrogen monoxide can also catalyze this reaction. In that case, the reactions are flipped. If nitrogen monoxide catalyzes the reaction, okay, if nitrogen monoxide catalyzes the reaction, then what happens is that this reaction happens first. Okay, this reaction happens first, where NO reacts with half O2 to form NO2, and then the NO2 reacts with SO2 to form nitrogen monoxide and SO3. Okay, so you have the same overall process, but the reactions happen in reverse. Okay, the reactions happen in reverse. So you have the exact two reactions but happening in reverse, so you have the same overall equation. So this equation applies when this equation. So when we talk about this reaction over here, right, this particular reaction, it's the second step when NO2 is the catalyst, and it's the first step when NO is the catalyst. Separate 1 gram samples of sodium oxide, magnesium oxide, aluminum oxide, silicon 4 oxide or silicon dioxide, sodium chloride, magnesium chloride, Al2Cl6, aluminum chloride, and SiCl4, that's silicon tetrachloride or silicon 4 chloride, are added to separate beakers containing water and stirred. The number of beaker containing a white solid is Q. An excess of sodium hydroxide aqueous is then added to each beaker and stirred. The number of beakers now containing a white solid is R. Which row is correct? So the first question is, how many beakers contain a white solid Q? In other words, which of these compounds is insoluble in water? Which of these compounds is insoluble in water? We first add these compounds to water and stir it, and whichever beakers contain a white solid, right, that the number of those beakers is Q. Now sodium oxide will dissolve in water to form a solution of sodium hydroxide, so you won't see a white precipitate there. Magnesium oxide is very partially soluble in water. It's very partially soluble in water. It forms magnesium hydroxide, which is, you can say it's insoluble. Okay, it's very slightly soluble, so you will see a white precipitate of magnesium hydroxide. Aluminum oxide is insoluble in water. SiO2 is insoluble in water. Sodium chloride, magnesium chloride, and aluminum chloride are soluble in water. Sodium chloride forms a neutral solution. Magnesium chloride forms an almost neutral or a very slightly acidic solution, and aluminum chloride forms an acidic solution. Now silicon tetrachloride or silicon 4 chloride will react with water. Okay, it will react with water to form an acidic solution. Okay, it will react with water to form an acidic solution. Okay, because it undergoes hydrolysis. However, it will also form SiO2. So you will see a white solid in the beaker with silicon 4 chloride. Okay, this is a white precipitate. So even though it reacts with water, it does result in the formation of a white precipitate. This isn't the balanced equation. Okay, I'm just showing the products here. This equation is not balanced. Okay, but we will see a white precipitate. So we're going to see a white precipitate in 1, 2, 3, 4 of the beakers. Okay, so the answer has to be C or D. Then we add an excess of sodium hydroxide aqueous to each beaker and stir. The number of beakers now containing a white solid is R. So how many beakers contain a white solid after aqueous sodium hydroxide is added? Okay, now the magnesium hydroxide remains in solution, right? So if we talk about the magnesium hydroxide here, it remains in solution, right? The magnesium chloride, right, had dissolved in water, but because we're adding hydroxide, we're going to see a formation of a precipitate of magnesium hydroxide. Okay, Let's see the formation of a precipitate of magnesium hydroxide. Aluminum oxide is amphoteric, so it can react with alkali. Okay, aluminum oxide actually dissolves. Aluminum oxide actually dissolves because it forms a salt with this anion. Okay, it forms a salt with this anion. So the aluminum oxide will dissolve, and the Al2Cl6 also, the aluminum ions will form this anion or a salt with this anion, so it will remain soluble. Okay, and then the SiO2, okay, SiO2 only dissolves, okay, SiO2 does dissolve in sodium hydroxide, okay, dissolve in sodium hydroxide only if the sodium hydroxide is hot concentrated, okay, then you have a reaction, however in this case we're not using hot concentrated sodium hydroxide, so the SiO2 will not dissolve, okay. So in two of the beakers you're still going to see SiO2 in this beaker over here and in this beaker over here. So the answer over here is D. Which pair of alcohols are isomers of each other? Now we look at option A, we have butane 1-ol and 2,2-dimethyl-propan 1-ol. Now butane 1-ol is a 4-carbon alcohol, right, C4, whereas we have propan 1-ol, that's prop is 3, and then we have dimethyl, right, so that will be 2 methyl groups, so we have a total of 5 carbon atoms. So these can't be isomers, right, because isomers have to have the same molecular formula. You look at option B, butane 2-ol, again is C4H10O, and then we have propan 2-ol, and then we have 2-methyl. We have 2-methyl propan 2-ol. So we have 1 carbon here, methyl, plus 3, that's prop, which means we have a total of 4 carbon atoms, which implies that this alcohol also has the molecular formula C4H10O. Okay, so these two are isomers of each other. So just by looking at the name, you can deduce the number of carbon atoms and therefore the number of hydrogens and oxygens in each of these compounds. You can eliminate the others as well. Pentan 1-ol, pent is 5, right? Pent means 5, whereas prop is 3 plus 1 for the methyl, so that's 4. So this is a 5-carbon compound, this is a 4-carbon compound, and then D, again we have a 3-carbon compound here, that's prop, and then we have 2-methyl, that's 1 propan 2-ol, 2-methyl propan 2-ol, so that's 1 plus 3, that's a 4-carbon compound. How many chiral carbon atoms are there in one molecule of 2,2,4,5 tetramethyl hexane 3-ol? So we're going to draw this structure out. Okay, we're going to draw this structure out. We're going to start with the number of carbon atoms, right? We have hex, so that's 1, 2, 3, 4, 5, 6. That's our parent chain. It's hexane, so there's only single bonds, 3-ol. So there's an OH group on carbon number 3. So there's an OH group on carbon number 3. And then we have a methyl group on carbon 2. We have another methyl group on carbon 2. And we have methyl groups on carbons 4 and 5. Okay, so 1, 2, 3, 4, 5, 6. We have a methyl group here. Carbon 2, we have 2 methyl groups, CH3 and then CH3. In carbon 4, we have 1 methyl group. And carbon 5 we have 1 methyl group. Okay, so that's 2, 2, 4, 5 tetramethyl hexane 3-ol. Okay, so this is our compound. This over here is our compound. So how many chiral centers do we have here? Now in this compound, obviously none of the CH3 carbons are chiral carbons, right? This carbon is not chiral because it's bonded to 2 CH3s, 2 identical groups. Remember, a chiral carbon is a carbon that's bonded to 4 different atoms or groups of atoms, right? So this guy is a chiral carbon atom. It is bonded to an H and OH, this entire thing here, and then this entire thing here. So it's bonded to 4 different atoms or groups of atoms. And then this carbon over here is also a chiral center. Right? It's bonded to an H, a CH3, this entire group on the left, and then this entire group on the right. Again, this carbon is not chiral because it's bonded to 2 identical CH3. So we only have 2 chiral centers here. Which pair of reagents react together in a redox reaction? The first reaction is a reaction between propene and bromine. Now in this reaction, we have electrophilic addition taking place, right, where we get 1,2-dibromopropane, right? So we get CH3CH Br CH2Br, right? This is electrophilic addition of bromine, and this is a redox reaction, okay? Whenever something is converted from the elemental form to a compound, it will always be a redox reaction, right? Because bromine over here has an oxidation number of 0, right, in the elemental form, and in this form over here, bromine would have an oxidation number of -1, okay? So whenever something is converted from elemental form to be part of some compound, it will always be a redox reaction, okay, because the oxidation number will always be 0, okay, in the elemental form, and then non-zero in the compound, right? So here bromine is undergoing reduction, it is the oxidizing agent, okay, and the propene is being oxidized, okay, it is the reducing agent. So the answer here is A. The structure of santonine is shown. Santonine is first treated with warm dilute sulfuric acid. The product of this reaction is treated with cold dilute acidified KMnO4. A final product Q is obtained. How many atoms of hydrogen in each molecule of product Q will react with sodium metal? When we first react this compound with warm dilute sulfuric acid, we have acidic hydrolysis of the ester. Okay, we have acidic hydrolysis of the ester, right? So the ester linkage breaks. The ester linkage breaks. Okay, what we end up getting over here is an alcohol group, right? A hydroxyl group and a carboxyl group, right? So the ester is hydrolyzed, okay, and we get a carboxylic acid and an alcohol. Okay, we get a carboxylic acid and an alcohol. Then we react the product. Okay, this is the product. We reacted with cold dilute acidified KMnO4. Cold dilute acidified KMnO4 is used for the weak oxidation of alkenes. It's used for the weak oxidation of alkenes. So what happens here is that we have the addition of two OH groups, right? The formation of diols, right, across each of these double bonds. Okay, so the addition of two OH groups, that's the weak oxidation of alkenes. Okay, what we end up getting is that the pi bond in each of these alkene groups breaks, right, and we end up getting diols. Okay, so we get an OH here, an OH here. Okay, we get an OH over here, and we also get an OH over here, right? This is our final product Q. Okay, so this over here is our final product Q. How many atoms of hydrogen in each molecule of product Q will react with sodium metal? Sodium metal is used as a test for the OH group. Okay, so the hydrogen atom in each of the OH groups will react with sodium metal, right? The hydrogen atom in each of the OH group will react with sodium metal to form the salt, okay, to form the salt and hydrogen gas, right? So over here, we're going to get salt and hydrogen gas. Okay, so over here we have 6 hydrogen atoms in each molecule that will react, right? Because we have 6 OH groups. We have 6 OH groups, 1, 2, 3, 4, 5, 6. Okay, the 6 hydrogen atoms from each molecule will react to form 3 molecules of hydrogen gas. Every one OH group results in the formation of half a mole of hydrogen gas, okay, or half. 1 mole of this, 1 mole of OH results in half a mole of H2. So you have 6 moles of OH in 1 mole of this compound, we get 3 moles of hydrogen gas. So 6 of the hydrogen atoms will react. So the answer is D. Compound R can be formed from 1-bromopropane using a nucleophilic substitution reaction followed by an oxidation reaction. What is the identity of R? So 1-bromopropane, I'm going to draw the skeletal formula as this guy, right? This is 1-bromopropane. And we're saying that if we react 1-bromopropane using a nucleophilic substitution reaction, right, and then we oxidize that product, what compound can we make? So let's look at the first option. Can we make propanoic acid from 1-bromopropane using this 2-step procedure? So can propanoic acid be made from an oxidation reaction? That's the first question. So here I have propanoic acid. So is there something I can oxidize to make propanoic acid? Well, the answer is yes. I can oxidize a primary alcohol, specifically propan-1-ol. I can oxidize propan-1-ol to make propanoic acid, and I can make propan-1-ol from 1-bromopropane using a nucleophilic substitution reaction, right? If I react 1-bromopropane using NaOH aqueous, right, and heat under reflux, I get a nucleophilic substitution reaction. That's the hydrolysis of 1-bromopropane to get propan-1-ol, and then propan-1-ol can be oxidized using acidified manganate 7 or acidified dichromate 6 and heating under reflux, okay, to form the carboxylic acid, that is propanoic acid. So the answer is A. 3 colorless liquids of the following formula are contained in separate unlabeled bottles. We have propanoic acid, we have 2-hydroxypropanoic acid, and we have this guy over here. Okay, this is a ketone and a carboxylic acid. This is actually 2-oxopropanoic acid. Which two tests carried out in separate samples of each liquid will successfully identify each liquid? Now over here, test number 1 is sodium hydrogen carbonate. Now NaHCO3, right? NaHCO3 will react with all three. Okay, it will react with all three. I'm going to call this compound 1. I'm going to call this compound 2. And I'm going to call this guy over here compound 3. The sodium hydrogen carbonate will react with all three because all three compounds have a carboxyl group, right? All three compounds have a carboxyl group, right? Sodium hydrogen carbonate reacts with carboxylic acids to form salt, carbon dioxide, and water. The second test, that is 2,4-DNPH. 2,4-DNPH is used as a test for carbonyl compounds, right? That is aldehydes or ketones. Okay, aldehydes or ketones. So 2,4-DNPH will only react with compound 3 because we have a ketone over here, right? We have a ketone over here, so it will only react with compound 3, which means that we will not be able to distinguish between 1 and 2. We will not be able to distinguish between 1 and 2. Okay, so A wouldn't work. Okay, option A wouldn't work over here. Next, we have option B. Again, we're using sodium hydrogen carbonate. All three will react, right? Compounds 1, 2, and 3 will react. And Tollens reagent is a test for the CHO group. The test for the CHO group. So neither of these compounds will react. None of them will react. Okay. None of the compounds will react here. So again, we can't use these two tests to distinguish between the compounds. What about warm acidified dichromate? Now, acidified dichromate will not be able to oxidize the carboxylic acid, and it will not be able to oxidize a ketone either. So acidified dichromate 6 will only react with compound 2, right? The secondary alcohol will be oxidized to a ketone, and 2,4-DNPH will only react with compound 3. 2,4-DNPH will only react with compound 3 because that's the only compound that has an aldehyde or a ketone. So we can use these two tests to distinguish between the three compounds, right? Compound 1 won't react with either. Compound 2 will react with dichromate 6, and compound 3 will react with 2,4-DNPH. So if there's no reaction with either, we know it's 1. If it only reacts with dichromate, we know it's 2. And if it only reacts with 2,4-DNPH, we know that it's compound 3. Okay, so the answer here is C. An alcohol X reacts with a dicarboxylic acid Y to form a double ester Z. The diagram shows the structure of the ester. Which row about the reactants forming ester Z is correct? We want to identify the class of the alcohol X and the shape of the ring in Y. So first we're going to look at the alcohol in X, right? We can determine the alcohol by first looking at the ester linkage, right? It's the bond between the C double bond O and the oxygen, that single bond that forms when the ester forms, right? So this was your dicarboxylic acid, or this part came from the dicarboxylic acid, and then these two ends came from the alcohol, right? So this used to be an OH group, right? This used to be an OH group. So the alcohol over here is this guy. This is propan-2-ol. Propan-2-ol is a secondary alcohol, right? The carbon with the OH is bonded to 2 carbons and 1 hydrogen. If it's bonded to 2 carbons, it is a secondary alcohol. So the answer has to be A or B. And then what about the shape of the ring in Y? Is it planar? We have tetrahedral carbons. We have a 6-carbon ring, but each of the carbon atoms is bonded to 4 different atoms or groups of atoms. We have two hydrogens here, we have two hydrogens here, we have a hydrogen, and then obviously we have the two hydrogens here and the two hydrogens here. So each of the carbons over here has a tetrahedral geometry. So then is this ring planar or non-planar? This ring will actually follow this sort of seesaw or like bent pattern. Okay, it's not going to be a flat ring. Okay, it's not going to be a flat ring because of the tetrahedral geometry of the carbon atoms. Okay, each of the carbon atoms is tetrahedral geometry, which means that the ring is non-planar. Okay, so the answer is A. Okay. W reacts with alkaline aqueous iodine to form a yellow precipitate and CH3CH2 CO2 minus ions. Which row identifies W and the yellow precipitate? Now this is the iodoform reaction. Okay, this is the iodoform reaction. So the yellow precipitate is triiodomethane. Okay, triiodomethane, that is CHI3, which means that the answer has to be A or C. Okay, it has to be A or C. So it can't be B or D. Now, in the iodoform reaction, because we're getting this triiodomethane, right, the other product has one lesser carbon atom than the reactant. Okay, I'll repeat. We get a one carbon product here, that's triiodomethane, and the other product will have one carbon atom lesser than the original reactant. Okay, so in this case, we're getting this 3 carbon product and this 1 carbon product, which means that the original compound had 4 carbon atoms. The original carbon had 4 carbon atoms, right? That gave you a 3 carbon and a 1 carbon product. Okay, so which of these has 4 carbon atoms? Is it butanone or propanone as your initial reactant? It is butanone, right? Butanone, but means 4. So the answer over here is A. Okay, the answer over here is A. And I'll show you what happens here, right? Butanone is CH3CO, CH2, CH3. Remember, the iodoform reaction is a test for this CH3CO group, right? So what happens here is that this CH3 breaks off, right? This CH3 breaks off and it becomes triiodomethane, and then this guy over here becomes a salt of the carboxylic acid, right? With one fewer carbon atom than the original reactant. Okay, so we get propanoate ions. Ethanol reacts with hydrogen cyanide in the presence of KCN to produce a hydroxynitrile. What is the first step in the mechanism of this reaction? This is a nucleophilic addition reaction. Okay, we have an aldehyde reacting with HCN, right? We have an aldehyde reacting with HCN, and KCN over here is the catalyst. Now in this reaction, the cyanide ion is the nucleophile. The cyanide ion is the nucleophile, and your initial source for the nucleophile is your catalyst, right? So KCN catalyst, it ionizes completely in solution, right? HCN is a weak acid, so it doesn't provide enough cyanide ions, right? So the KCN ionizes completely to form cyanide ions, right? Where the carbon has the negative charge. Okay, the carbon has the negative charge, and this nucleophile attacks the delta positive carbon. This nucleophile attacks the delta positive carbon. So the answer is B. Okay. Structural isomerism and stereoisomerism should be considered when answering this question. How many isomeric compounds with molecular formula C5H6O4 contain 2 CO2H groups and 1 carbon-carbon double bond? I'm actually going to solve this question. I'm going to solve this question on a separate sort of canvas, okay, on an empty canvas over here. Let's look at this question separately. Now we have compounds with the molecular formula C5H6O4, okay, and the question specifies that each of these compounds will contain 2 CO2H groups, 2 carboxyl groups, and a carbon-carbon double bond, right? Let's start with the simplest compound. Let's say we have a straight chain compound, right? Again, the molecular formula is C5H6O4. We have a 5 carbon compound. The carboxyl groups have to be at either end, right? We can't have carboxyl groups in the middle. So we're going to have a CO2H here, and we're going to have a CO2H here. Now we obviously have to have a carbon-carbon double bond. Now can we have a carbon-carbon double bond here or over here? So it's not possible to have double bonds over here or here, because if you notice, this carbon atom is already making 4 bonds, right? It's already making 4 bonds, double bonded to an oxygen, it's bonded to an oxygen here, it's bonded to a carbon here. So you can't have a double bond here, you can only have it somewhere in the middle over here, right? So you can either have it here or here, and it doesn't matter where you put it, right? Because it's symmetric. So if you put it here, or if I was to put it over here, right, it would be the exact same thing. It would be the exact same thing, right? So whether it's here or here, okay, it's the same thing. So this is one of the structural isomers that we can have. This is one of the structural isomers that we can have, right? We have a CH2 here, and then we have a CH and a CH. Now, will this structural isomer exhibit stereoisomerism? Will it exhibit stereoisomerism? This particular structural isomer will exhibit stereoisomerism, because if you look at the double bond, this carbon is bonded to two things, right? It's bonded to a hydrogen and it's bonded to this entire group. And this carbon is also bonded to two different things, bonded to a hydrogen and this entire group. So this particular structural isomer will exist in the cis and trans form, right? There could be a cis or a trans isomer for this particular structural isomer. So there's going to be two different compounds that have this structure. There's going to be two different compounds that have this structure, right? The cis isomer and the trans isomer. And this is the only structural isomer that we can get with a straight chain. Okay, this is the only straight chain possibility, right? Because we noticed that the double bond can't go here, so it can only go on over here or here, right? And those two are the same. And then obviously we have the cis and trans form of this. So now we have to look at branched isomers, right? So we're going to have a 4 carbon chain. We're going to have a 4 carbon chain, right? With a 5 carbon chain, we only had one possibility. If you look at a 4 carbon chain, right, what we have is, again, the carboxyl groups go on either end. Okay, the carboxyl groups go on either end. Now this is a branched chain, right? So we can have a branch on this carbon, or we can have it on this carbon. And again, that would be the exact same thing. Whether it's here or it's here, it's the exact same thing, right? And then of course, we are going to have a double bond over here, right? We're gonna have a double bond over here. Again, the double bond can't go here or here, okay? So then this is another possible isomer that we have, right? So we have CH3 here, right? We have a CH over here. Does this structural isomer exhibit cis-trans isomerism? This again exhibits cis-trans isomerism, right? This carbon is bonded to a CH3 and this entire group, and this carbon is bonded to a hydrogen and a CO2H as well. So again, we're going to have the cis and trans form for this isomer, right? So for this particular structure actually exists in as two different isomers, right? The cis isomer or the trans isomer. Now, are there any other possibilities with the 4 carbon chain? Okay, again, if we look at the possibilities, right? Let's draw it out again. Again, the carboxyl groups have to go on either end. The carboxyl groups have to go on either end. The branch has to go here, right? The branch has to go over here. Instead of having the double bond over here, we can also have the double bond over here, right? If we have the double bond here, then this would be a CH2, right? And then this would also be a CH2. Now, this structural isomer, does it exhibit stereoisomerism? Again, we have to consider cis-trans and optical isomerism, right? In the first case, we had cis-trans. We didn't have any optical. There's no chiral centers. In the second case, again, we had cis-trans. We didn't have any optical, right? Because again, we didn't have a chiral center. What about over here? Do we have stereoisomerism here? Does this structure exhibit stereoisomerism at all? Does it exhibit cis-trans? No, it doesn't, right? Because this carbon is bonded to two identical hydrogen atoms. There's no cis-trans here, right? And then there's no optical either because there's no chiral center, right? So this is actually just one compound, right? Only one compound has this structure over here, okay? This does not exhibit stereoisomerism, so it doesn't exist as a pair of stereoisomers, okay? So far we've identified five different isomers that have this molecular formula, okay, containing two CO2H groups and one carbon-carbon double bond, right? These are the only two possibilities, or the only three possibilities rather, that we have with a 4 carbon chain. The only two structures, right? One of them exhibits cis-trans, and then lastly we're going to look at a 3 carbon chain, right? Now we look at a 3-carbon chain, right? We have again CO2H on either end, right? Now we can't have a double branch here. The reason we can't have a double branch here is if you look at each carbon atom, okay, each carbon atom is already making 4 bonds here. So there's no space for a double bond, right? We already have 5 carbon atoms and there's no space for a double bond. But we can still have this 3-carbon chain. We can still have this 3-carbon chain. Again, remember the parent chain will have both the carboxyl groups, right? It'll have both the carboxyl groups. We can still have this 3-carbon chain. And then we can have a single branch with 2 carbon atoms. We can have a single branch with 2 carbon atoms like this. Now over here, we can't have the double bonds here. We can't have the double bond here. We can't have the double bond here. But we can have a double bond here or here, right? We can have a double bond here or we can have a double bond here. So if we look at those two possibilities, right? If we look at those two possibilities, one possibility that we have is we have a double bond here, right? Then we have a CH and a CH3. And the other possibility is if we have a double bond here, then we have a CH2 here, we have a CH here, and then we have a hydrogen here. Okay, now this guy doesn't exhibit cis trans isomerism, right? Because this carbon on the double bond is bonded to 2 identical groups, right? This carbon on the double bond is bonded to 2 identical CO2H groups. So no cis trans isomerism and no chiral center. So this structure is actually just one isomer, right? It doesn't exist as a pair of stereoisomers. And then this guy over here also doesn't exhibit stereoisomerism, right? Because we have a CH2. So there's no cis trans isomerism. There's no cis trans isomerism. And you might think there's a chiral center. However, if you notice, this carbon is actually bonded to 2 identical CO2H groups. So this is not a chiral center either. So again, this particular structure is just one isomer, okay? It does not exhibit stereoisomerism, or it does not exist as a pair of stereoisomers. The total number of isomers then that we have is 2 plus 2, that's 4, 5, 6, and then 7. So the answer here is C. Okay. So the answer to question number 35 is C. Okay, we have 7 isomers with the molecular formula C5H6O4 containing 2 carboxyl groups and a carbon-carbon double bond. Compound X reacts with ethanoic acid in the presence of an H plus catalyst, okay, that's basically acid, to produce the compound shown. What is the molecular formula of compound X? Now this is the product of the reaction between compound X and ethanoic acid, right? And we can clearly see that this part over here came from the ethanoic acid, right? Because we have an ester linkage here. So the product here is an ester linkage, right? And this guy came from the ethanoic acid, right? So this came from the ethanoic acid, CH3CO2H, right? So compound X was an alcohol, right? Compound X was a compound that contained an OH group over here. Okay, it contained an OH group over here, and then it obviously also has this ketone group. So compound X then is CH3CO, CH2, CH2, right? CH3CO, CH2, CH2, and then this was an OH, right? And this guy reacted with ethanoic acid to form this ester, right? Using an acid catalyst. So then what's the molecular formula of compound X? Compound X has 1, 2, 3, 4 carbons. So it's C4, right? And then it has 8 hydrogens. 3 plus 2 plus 2 plus 1, that's 8. And then it has 2 oxygen. So it's C4H8O2. Okay, so the answer is D. 2-bromopropane reacts with hot ethanolic sodium hydroxide. Which substance is the major product of this reaction? Now 2-bromopropane is this guy, right? We have a 3-carbon compound, that's propane, and then we have a bromine on carbon number 2, right? And when this guy reacts with ethanolic sodium hydroxide, what type of a reaction takes place? When a halogenoalkane is reacted with sodium hydroxide and ethanol, right, we get an elimination reaction. Okay, we get an elimination reaction where the halogen is removed, okay, the halogen is removed, and the hydrogen from the neighboring carbon is removed. And we get a double bond between those two carbons. Now over here, whether you remove this hydrogen or this one, it doesn't matter, right, because they're identical. So the product that we get here is propene, right? We get CH3CH, CH2. So the product of this reaction is D, okay, that's propene. Which compounds can be used to make Y in a single step reaction? Y is propanoic acid. Y is propanoic acid. That's CH3CH2 COOH. Can propane nitrile be converted to propanoic acid in a single step? Propane nitrile is CH3 CH2 CN. Okay, CH2CN, right? It's a 3-carbon nitrile, that is propane nitrile, right? 1, 2, 3 carbons, that's propane, and then nitrile. So can propane nitrile be converted to propanoic acid in a single step? It can, right? This is acidic hydrolysis of nitriles. Acidic hydrolysis of nitriles. We can just use dilute HCl and heat under reflux, right? And the propane nitrile will be converted to a carboxylic acid, that is propanoic acid. So 1 is definitely correct. 2 is a 2-carbon nitrile, so it can't be converted into propanoic acid, right? It's a 2-carbon nitrile, so it won't make a 3-carbon acid when we hydrolyze it. We know that the answer has to be A or B, of course, because 1 is correct, right? So we can eliminate C and D from the first choice here. And then propyl ethanoate, right? This is an ester that we can hydrolyze, okay? But propyl means we have this alcohol part is 3 carbons and then the acid part is 2 carbons, right? Propyl and then ethanoate, right? So here we would actually get ethanoic acid. We would get ethanoic acid, right? Not propanoic acid. So it's not 3. So the answer must be 4, right? We have ethyl propanoate, right? This propanoate means that we get propanoic acid. So we look at ethyl propanoate. Propanoate is this guy, right? And then we have a 2-carbon alcohol, right? So when we hydrolyze this ester, again we can use dilute acid and heat, right? Acidic hydrolysis of esters, we're going to get propanoic acid and ethanol. Question number 39 says the monomer buta-1,3-diene can undergo addition polymerization in various ways. 2 of the polymers that can be made are called cis polybuta-1,3-diene and trans polybuta-1,3-diene. In these names, cis and trans have their usual meanings. What is the structure of the repeat unit of cis polybuta-1,3-diene? When we talk about buta-1,3-diene, right, we have this compound. We have a 4-carbon compound and we have a double bond on carbons 1 and 3. We have a double bond on carbons 1 and 3. So we have a CH2 here and we have a CH, a CH and a CH3. Okay. Now, when this guy polymerizes, okay, right, we have when a diene polymerizes, okay, what we get is along the main chain we get a 4-carbon repeat unit. Okay, we get a 4-carbon repeat unit, and what happens here is this. Okay, when we talk about the repeat unit here, okay, this is what we get. What we get is we get CH2, then we get a CH, double bond CH, and then a CH2. Okay, this is called a conjugated dienes. Okay, when conjugated dienes polymerize, conjugated dienes are where we have alternating double bonds. So the double bonds are 1 carbon apart, right? We have a double bond, a single bond, and then a double bond. These are conjugated dienes. When these guys polymerize, what happens is that at the ends of this 4-carbon chain over here, okay, I'm going to take this 4-carbon section that contains the 2 double bonds, okay, and the polymer, right, the repeat unit or the polymer will have a double bond in the middle, and you're going to have continuation bonds. On the left and the right. Okay, so this CH2, this double bond will come here, and then this CH2 can bond to the next alkene, and then again this double bond over here goes away, right? And then this CH2 can bond to the next alkene. Okay, so this will be our repeat unit. So when we look at this repeat unit, the repeat unit only has 1 double bond, right? So if you had a regular alkene, the repeat unit has no double bonds, right? The polymer has no double bonds. If you have a diene, then the polymer has one double bond. So one double bond becomes 0, two double bonds becomes one double bond. Okay, so it has to be B or C. And since we're talking about the cis form, right, the answer must be C. Okay, the answer must be C because the carbon chain is on the same side of the double bond instead of alternating, right? Cis means on the same side, whereas trans is alternating. So the answer is C. So the thing to note here is that in this particular case, what you should know is that if you have a diene, then the polymer, the repeat unit will only have one double bond. Okay, if the monomer has two double bonds, the repeat unit will only have one double bond. It will be in the middle. Okay, it will be in between where the two double bonds were originally. So the two double bonds were here. The new double bond will be in between the two, right? And where those two double bonds were, right, those ends will become your, those ends will be where your continuation bonds are. So once you know that only has one double bond, we can easily eliminate A and D, okay, because the polymer, the repeat unit won't have two double bonds. And then you just have to identify the cis form, which is C. In the mass spectrum of a compound Z, the relative abundances of the M and M plus 1 peaks are in the ratio 13:1. What is compound Z? Now the relative abundances of the M and M plus 1 peaks, okay, can be used to find the number of carbon atoms. Okay, these relative abundances can be used to find the number of carbon atoms. Okay, we're going to use the letter N for the number of carbon atoms. The ratio of heights of the M and M plus 1 peaks is equal to 100 over 1.1 N, okay, where N is the number of carbon atoms. Now they've given us the ratio of the heights of the M and M plus 1 peaks. That's 13:1, right? So that's just 13. And 13 is equal to 100 divided by 1.1 N, which means that N is equal to 7, rounded to the nearest whole number, which means that the compound has 7 carbon atoms. Okay, the compound has 7 carbon atoms. Now if you look at option A, it's butanoate, so that's 4 plus 4, so that's 8 carbon atoms. So that's 8 carbon atoms, so it's not A. B is hexane 3-on, that's 6 carbon atoms, right, hex, so it's not B. C is trimethylhexane, 2,2,3 trimethylhexane, so that's 3 plus 6, so that is 9 carbon atoms, so it's not C either, so it must be D, right? We have 3,3 dimethyl, dimethyl is, methyl is 1, dimethyl is 2, and then pentan 1-all, pent is 5, so we have a total of 2 plus 5, which is 7 carbon atoms, so the answer is D.